Okay, so I'll start by reviewing what we did last time. Last time we looked at the Higgs sector, and today we'll continue doing that. The Higgs sector of the MSSN. So what we did in particular was to look at the mass matrices, and without repeating last time's calculation, I'll just summarize for you what the answers were. First of all, we had for the charged, so how many Higgs did we have? We had two doublets, that makes altogether two charged Higgs and their antiparticles and 4 neutral Higgs. Okay, altogether 8 real particles if you like. But the charged Higgs of course can more naturally be considered as two complex particles. One is the H1 minus and the other independent charged Higgs is the H2 plus. Okay, so the mass matrix will be a 2 by 2 matrix in the basis H1 minus and H2 bar minus, and then here H1 bar plus and H2 plus. Because H2 occurs naturally as plus and H1 occurs naturally as minus. So there is a matrix in between, and the matrix turns out to be this notation is not very convenient, it's the blocking of the whole board. So let me just write for H1 minus H2 plus the mass matrix is mu plus G2 squared upon 4 B1 B2 into tan beta 1 by tan beta. This is what we derived last time. And the eigenvalues of this matrix are 0 and 2 upon sin 2 beta, which is the same as the sum of these two. Okay. And just to remind you what everything is, tan beta is V2 over V1, where V2 and V1 are the waves of the two different Higgs. And those appear here also. G2 is the coupling constant of SU2, and T is a soft breaking parameter, and it's very important in all this discussion. So we conclude from here that there's one Higgs, so one of these, the one that's massless, is really a goldstone, and that gets absorbed. It's charged goldstone, and it's complex conjugate, and it gets absorbed by the W plus and W minus. That's sort of obvious because the Higgs mechanism has to work that way. The other one, because the name is going to be a genuine physical observable charged Higgs boson, and it gets the name H plus, capital H plus and minus. So we learn that m squared of H plus and minus is equal to B mu plus, now this thing I can more fruitfully write in terms of the mass of a physical particle, which is the W. So actually it can be written as B mu B mu over sine 2 beta in the first term. That's this 2 over sine 2 beta times that. The other thing, which is 2 over sine 2 beta times this, if you work it out, you'll find that it's exactly the mass of the W squared. So this comes to mass of W squared. Okay. Mass of the W is just given by G2 squared by 4 B1 squared plus B2 squared, I believe. And it's just the same relation as in the standard model, with V1 squared plus V2 squared in place of V squared for the single standard model Higgs. And this thing hopefully is the same as this stuff times sine of 2 over sine of 2 beta, except I may have got a 2 factor wrong. Not very happy about this. 2 upon, no, this is correct. 2 upon sine 2 beta is the same as sine beta cos beta, and if I take v1, v2 and divide by sine beta cos beta, it's quite an easy exercise. You are encouraged to try it. So this is the answer for the Higgs plus and minus. Good. So that takes care of all the charge Higgs. Okay. The next thing we found was that there were 4 neutral Higgs, but we could diagonalize the real part of H1 and H2 naught and the imaginary part of H1 and H2 naught separately. We did the real parts last time, and we found for those a very similar mass matrix. So this was real H1 0 and real H2 0. So H1 and H2 are complex doublets. So each of the doublets has a neutral part, and each of the neutral parts has a real part. So that's these two. And here we found the mass matrices to be very simply B mu into tan beta 1 and 1 by tan beta. So the eigenvalues are precisely the same, except that this time it's a mass matrix for some real particles, and therefore there's a real Goldstone, which is neutral, obviously, being real, and a real Goldstone just gets absorbed by the Z boson to make its mass. So that takes care of that, and that leaves a Higgs with this mass multiplying B mu, and that Higgs that it leaves is called A. So Ma squared is equal to 2 B mu upon sine 2 beta. Alright. So that's a neutral Higgs, and this I had done last time. The third Higgs, so the last Higgses are the ones which come from imaginary parts of H10 and H20. So there are imaginary parts here. Here it turns out the matrix is considerably more complicated. But after all, it's hardly a big problem to write it. It's just that it's not illuminating. So instead of that, I'll just give you the mass eigenvalues. And the important point here, there are 2 important points to note here. Sorry, I think, did I do something wrong? This is real. This is, thank you. It's the real guys that I did before and the imaginary, the imaginary guys I did before and the real guys I did now. Okay? So sorry, please correct that. The imaginary H10 and H20 are one of them a Goldstone mode and the other is the A. Okay? In fact, I think probably A might stand for axial vector. It's a CP odd state. And the real parts are what are more complicated. So is that clear? Whatever I called real earlier was supposed to apply to the imaginary parts. Okay? The real ones are more complicated. And there's an interesting fact about it. You see, these are the ones that get waves. Okay, imaginary, because we saw that the waves of H1 and H2 are real numbers V1 and V2. Okay, and of course they occur in that component which is neutral. So obviously H1 plus minus and H2 plus minus don't get waves because they're charged. Among the neutral ones, the imaginary ones don't get waves. That's our conventional choice, and it's the real ones which get waves. Okay, so these are the ones which do get waves. And their masses come out, so eventually after we diagonalize, we get 2 particles, both of which are massive. Remember, we didn't need any more Goldstones. We already got 3 Goldstones out of 8 Higgs. Okay, and we only wanted to make Z and W plus minus massive. So we certainly don't need any more Goldstones. So both of these should be massive, and they are called H and H. This is notation in the literature. Okay, this H, to distinguish from those, could be called H naught. There's a reason for that. Both are neutral anyway, and this will just simply be called small h. So let me not write down the mass matrix, but just the answer for the mass eigenstates after diagonalization. So we find that the little h has a mass which is convenient to write in terms of this one. This actually plays a key role. So this, instead of writing these parameters, we just describe it as ma square, and we'll write all the other Higgs masses in terms of this Higgs mass as one of the parameters. So it turns out to be this plus the Z mass square minus the square root of ma square plus mz square minus for ma square mz square cos square 2 beta. And the other one, as you probably guessed already, is the same thing with a plus sign. So there is a quadratic equation from that matrix which I didn't write, and its two roots are these, the eigenvalue equation for that. And we've chosen the sign in such a way that this is out of the positive square root. So we see that mh is always less than m of capital H. This is our convention in how we label them. Okay. Out of these two, since both are massive, one is going to be lighter than the other, and we'll call that lighter one small h. So now hopefully the Higgses are starting to take on some personality. There are 5 of them, 2 are charged, so they are separate, capital H plus minus. 3 are neutral. Out of the 3 neutral, 1 occurs by itself because it's a partner of a goldstone, which when we diagonalize the mass matrix, and its value is useful as a parameter governing all the Higgs masses. In fact, right away you see that I can replace it here. This quantity by this equation is ma square. So the charged Higgs I can write as having a mass ma square plus mass of the W square, and this I treat as an independent parameter. You see it's proportional to the soft breaking term P, which we'd argued many times that it's very important in getting the Higgs mechanism to happen. And finally, these two neutral Higgs also depend on Ma as well as the mass of the Z, which is fixed, and beta, nothing else. So it's a very convenient parameterization. And we'll see that we can extract a lot of physics from these formulae, limited only by the fact that these are 3-level formulae and they may get important loop corrections, which we'll turn to next. So we'll be assuming for the moment that these are valid and see what physics you can derive. And it's actually extremely interesting and extremely well connected to things that one would see in experiments. We'll get bounds, various kinds of bounds on the masses of the observable Higgs. And I've already stressed before that this spectrum of 5 Higgs particles is characteristic of the MSSM. Okay? And only one Higgs, real Higgs, is what you'd observe in the standard model. And there will be some limits, obviously, in which the MSSM will behave like the standard model, and we'll see what are those limits. Those are some limits which decouple most of these things, leaving behind one which looks just like the standard model Higgs. So let's do that analysis. But before that, I need to just mention how, so there's one important parameter in this, which is how you get the mass eigenstates out of the original Higgses. So, yes.
Before going to the end, remind briefly how these do not depend on the soft breaking mass terms and m1 square and m2 square and on, which just depend on B and D.
M1 squared and M2 squared. Yes.
You solved for them.
Yeah. There was an equation which was the minimizing equation for the potential. Okay. In that potential, M1 squared and M2 squared appear on one side, and the soft breaking term B mu appears on the other side. But and also the Z or W or Z mass appear in that. And it turns out then that equation has the form that we can eliminate the soft breaking masses, leaving behind only a dependence on B. So in fact on B, therefore. So really B and beta govern everything. But that precise equation for minimizing the potential has to be revised if we add loop corrections, because then we should minimize the effective potential. So then things will be quite different. Okay. Now one quick observation here is that we need to actually perform a rotation to extract out the eigenstates defined by these, and it's good for me to tell you what it is. So remember, I have to tell you. So let me write the equation and you will see what it means. G plus minus are the charged Goldstone modes. Okay, and along with them came H plus and minus, which are these massive Higgs. So these are going to be some linear combinations of small h1 and small h2, their charged components. But what are those linear combinations? Well, it's pretty easy to see because it just has to come from the matrix which diagonalizes. It's just what diagonalizes that 2 by 2 matrix, which I wrote earlier, which had tan beta 1 by tan beta 1 and 1. Okay, that's a very easy matrix to diagonalize. And this is, so the rotation we have to perform to diagonalize it is just a rotation by the angle beta. So in other words, if beta was 0, which means the second Higgs didn't have a wave, but only the first Higgs had a wave, everything we're doing here would go through, and the Goldstone would be entirely made up of H1s, and the massive Higgs would be entirely made up of H2. Okay. So this is just the rotation which defines for me capital H plus and minus in terms of the original fields in the Lagrangian. There is a similar rotation for the neutral ones corresponding to the imaginary part, and that defines for me G naught and A. So G naught is the neutral Goldstone and A is this one. So these actually, if you remember, the matrix was quite the same. Just the coefficient was different, but the matrix was the same. So the rotation is exactly the same. So this actually is minus im H1 0 cos beta plus im H2 0 sin beta. This is essentially the same equation as above. This is im H1 0 sin beta so again we see that if beta was 0, then the neutral Goldstone would be the imaginary part of H1, and in fact therefore H1, 3 of its components would be Goldstones. Okay, of course you can see what's happening physically, because if V2 is 0, then we are not able to give mass to the up quarks. Okay, the Higgs H2 was there to give mass to the up quarks, while the Higgs H1 gives mass to electrons and to the lower electrons, not the neutrinos, the electron tau, and to the down type quarks, the downstream at bottom. So if you only had that Higgs in the problem and only gave that one a wave, then those quarks would get masses, and that Higgs would behave like the standard model Higgs, except that it wouldn't be coupling to the up type quarks. And so that Higgs doublet, 3 of its modes would become Goldstones, and one would be the physical observed Higgs. Okay, and that physical observed Higgs in that case would be A. But that's of course not, that's an extreme limit, V2 equals 0, which is completely unrealistic, of course, because all the down type quarks have a mass. So V2 cannot be 0 for that reason. If you remember, it was supersymmetry which prevented the Higgs H1 from giving a mass to the down type quarks. So in the MSSM, we are obliged to have a non-zero V1 and V2. Okay. Finally, the rotation which gives these two particles, small h and capital H, which are somewhat neutral Higgs, but this rotation is a little more complicated, and it actually involves a new angle which I'll need to define here. So this involves real part of H1 naught, but I have to subtract from it its own wave. It's the real part of H1 naught which gets a wave V1 by root 2. So I subtract that wave, then it's the shifted field, and it's this field which participates in this kind of rotation. So it's this times, well, to keep the pattern, it doesn't matter much, this times cos alpha plus real H2 naught minus its wave sine alpha. But alpha is a new angle because this matrix does not come out to be tan beta 1 over tan beta like in the other two cases. So I have to define alpha for you. There. So alpha can be defined by various equations, all of which are useful. The primary equation is that sine, well, it depends what you want it defined in terms of. So sine 2 alpha is most conveniently expressed in terms of the masses. These two guys, masses of the H, small h and capital H. And then sine 2 beta. But another equation, which obviously can be derived from this one, conveniently expresses tan of that rotation alpha, but in terms of the masses of the A and the Z. Okay, of course, these are, as I said, these can be derived from each other because after all, these two guys are given in terms of masses of the A and Z as well as beta. So if you just plug that in, you can go from there. So this introduces a new angle alpha, which is the rotation angle which converts the real part of the two different standard model heats, their neutral components, into observable particles, which are mass eigenstates, capital H and small h. Now we can make a few useful observations. One right away is that beta is between 0 and pi by 2 because tan beta is positive. Because tan beta is V2 by V1. But that means that sine of 2 beta is positive because 2 beta goes from 0 to pi and sine is positive along all of that. This numerator is positive. The denominator is also positive because remember capital H is the heavier of these two. So the whole thing is negative. So sine of 2 alpha is negative. That means 2 alpha goes from minus pi to 0, which finally means that alpha goes from minus pi by 2 to 0. So alpha, you have to remember, is a negative angle between minus pi by 2 and 0. Okay. So now we can make some comments. So I hope this is clear. These are just the rotations we have to perform on the components of the original Higgs fields in order to get the 8 mass eigenstates, of which these are massless, Goldstone, and 2, 3, 4, 5 are massive, and those are observable. So I'll drop this out now. And we talk about different limits and different bounds on the Higgs mass spectrum. So partly that just consists of reorganizing this information in a way that's useful. So here are some comments. So one is that if MA goes to 0, that will happen if we put this soft breaking parameter B mu to 0. Then notice that MH also goes to 0 because MA going to 0 means this term vanishes, then this square root becomes the same as this, and so it goes to 0. Okay. Not only that, the other one, MH, this guy, then becomes the sum of these two equal terms as well as MA is 0, so it's really the sum of MZ squared twice times the half, so it goes to MZ. Okay. And finally, the charged guys go to M of W plus minus because this term goes to 0. So this is one interesting fact, or if you like, one interesting limit. In which the Higgs masses reduce into a particular formation to become, this is not necessarily a realistic limit, it's just a formal limit in this parameter space. 2 Higgses are extremely light, and 3 just have become exactly degenerate with the Z and the W. Okay, so that's one. So the conclusion we draw from this is that MA controls all the Higgs masses. I mean, it was already obvious from the fact that all the Higgs masses depend only on Ma as well as known quantities like Mw and Mz, which we are not allowed to fiddle with, as well as beta. Okay. Now more interesting relations are the constraints. So first of all, we notice that the top relation, the one for H plus and minus, tells us that this is greater than the maximum of Ma. So I don't have to put the square. That means the charged Higgs are heavier than the maximum of this neutral Higgs and the W boson. Okay, so they are in particular heavier than both. That means in a limit when Ma is very light, these will nevertheless be heavier than the W boson. In fact, we just saw that when Ma is 0, these become degenerate with the W boson, but for any other value of Ma, they are heavier. Okay, and in another limit, when Ma goes to infinity or becomes very large, then these guys will become even larger. Okay, so there is a lower bound for the charge Higgs. That's useful. Okay, now let's look at M of H, small h, from this formula. And let's see the range of values if we keep everything else fixed except beta and we vary beta. Okay. When beta is pi by 4, then cos of this of 2 beta is 0. Okay, pi by 4 means that V1 and V2 are equal. The waves V1 and V2 are equal, but then tan beta is 1. Okay, so in that case this term vanishes and this just cancels this, and so MH goes to 0. Okay, so we learn that for beta equals pi by 4, MH goes to 0. For the other limit, beta equals 0, in that case what happens is this becomes Ma squared minus Mz squared squared. Okay, when you take the square root, you get that MH is half of Ma squared plus Mz squared minus mod of Ma squared minus Mz squared. Is that clear? Now this thing is going to be Mz squared if Ma is heavier and Ma squared if Mz is heavier. Okay.
This is MH squared.
Sorry? Mh squared. That's it. Okay. So this is going to be, as I said, Mz squared if Ma squared is heavier and Ma squared if Mz squared is heavier. So it's the lighter of the two. Okay. So this is actually equal in this limit. It goes to the minimum of Ma squared and Mz squared. Okay. So we've looked at it in two limits, beta equals 0 and pi by 4. But this covers everything because from pi by 4 to pi by 2, which is the remaining range of beta, this thing just repeats because cos squared appears over there. Okay. So what happens is if we start at 0, then Mh squared starts at this value. Then as we tune beta to pi by 4 it goes to 0. Then as we tune it to pi by 2 it goes back to this value. Okay. So in other words, the bound is 0 less than Mh less than minimum of Ma and Mz. So here's a very precise bound. And this is perhaps the single most striking thing in this entire Higgs sector, because it says that the Higgs, one of the Higgs, this particular one, small h, is strictly bounded above by the Z mass. Okay, so if we believe this tree level consideration, Then we have an upper bound on the Higgs which doesn't have any counterpart in the standard model. Standard model Higgs can be much heavier, but one of the 5 MSSM Higgs has to be lighter than the Z. Okay. For the other Higgs, capital H, this guy, we can likewise find some bound, but it's again a lower bound, because you see that this one is the same as this with a different sign chosen over here, so it's likely that we'll get a lower bound, and in fact what you get is that MH is greater than max of MA and MZ. Okay. However, it's also bounded above by the value of square root MA squared plus MZ squared. So, but in particular, what's important is that it's bounded below. Okay. So, with this, you get a sort of picture that A can do what it's like. We think of its mass as a free parameter for the moment, but capital H and H plus and minus are all bounded below. This is the lower bound for H plus minus, and this is the lower bound for capital H. So, those are all the 3 heaviest Higgs, if you like. MA is free, and M and H, small h, is the lightest Higgs. And it's got a strict upper bound. Okay.
So, much lighter than MZ.
Yes. Much
Okay.
lighter. Okay.
I mean, experimentally, it will form Higgs.
That doesn't mean we haven't produced it, no? Finding a particle experimentally is not only a matter of producing, it's also a matter of detecting.
Experimental bound on the Higgs.
Yeah.
Heavily constrained.
Yeah. Well, of course, the other thing is that this is a 3-level constraint. So we'll first have to see what happens when we include loops, 1 loop corrections.
But the present experimental bounds are okay with this bound.
Okay, I'm not sure about that. If it's not this, it will still, this is, Z is around 90 GeV. I mean, it will be, the point is that somewhere around 100 or in the early hundreds, I think is still consistent with the experimental bound, could be wrong. But so, in that case, probably it will come by correcting this using the corrections, which are very important, and which we'll start discussing right away once we are done with this. Yeah, thanks for pointing that out. Okay, another relation you get is for beta, for this angle alpha. Okay, that doesn't seem very illuminating, so I won't write it. Okay, but instead what I'll do is I'll summarize these bounds by the following diagram. Here is MA, and here I'll indicate the range of values for small h and capital H. And the way we'll do it is we draw this line at 45 degrees, and then here we put the mass of the Z. And the claim is that this lighter one, small h, can lie in this, this is a horizontal line. So this is the region where MH can lie. Okay. Why is that? Because as long as MA is less than MZ is inside here, then MH has to be less than MA, so it's inside this triangle. But when MA becomes large enough to cross MZ, then the bound only says that MH has to be less than MZ, which is this fixed horizontal line. So MH lives inside this region. Okay? And likewise, sort of mirror image, capital H lives inside this region. Okay. It's bounded below by MZ, but when MA becomes larger, then it's bounded below by MA. Both of them follow from this bound and this bound. Okay, so are these pictures clear?
There's an upper bound. On image, there's an upper bound.
Yeah, I haven't plotted that. But the important thing to see is that if I crank up this MA to be very large, then MH has to keep going up to keep above this line. Okay. While however large it becomes, nothing has to happen to m small h. It just has to stay in this region. It doesn't get free to go higher. It's always bounded here, but the bound doesn't change asymptotically. Okay. So this brings me to something called the decoupling limit. This is useful to think of because it's a limit, as we just showed, where the entire Higgs sector of the MSSM turns into the Higgs sector of the standard model. Okay. Now, how can it do that? We have 5 Higgses, so obviously 4 have to become infinitely massive. But that's pretty easy to do because we saw that MA is the governing parameter, so let's send that to infinity. Okay. Of course, it never goes to infinity, but in practice, greater than 250 GeV will do this job. Okay. When we do that, of course, we note that these become infinitely massive too. Okay. This becomes infinitely massive too. But this one is always bounded by this thing, and that's because this one